Today's problem, find the acceleration of a block, speed before contacting the spring of the block, max spring compression, and the simple harmonic angular frequency and the simple harmonic position function of the diagrams from below. So what we have here seems to be a spring with a spring constant of 800 Newton over meters. We have then a 5-meter gap between the spring and a 4-kilogram block with a 50 Newton applied force at 30 degrees, and the kinetic friction in the surface is 0.20. So first, let's draw a free body diagram for this box right here. So we have the downward force mg, we have the normal force, and we have, since the force is pushing it this way, we have a friction that pushes back that way. So that's our force of friction. And we have a force at an angle here, so we have to break it into its horizontal and vertical components. So this is going to be F sine theta, and this is going to be F cos theta. So to find the acceleration, we have to remember the equation net forces of x equals ma acceleration of x. So to find the acceleration, it's the horizontal acceleration, so it comes from the horizontal force. So we have to first find out all the net horizontal forces acting on the object. Right now, as you can see, the net horizontal forces acting on the object is F cosine theta and the force of friction. And to find the force of friction, it's the equation kinetic friction times the normal force. Normal force in this case is mg minus F sine theta, which is going to come out to 4 times 9.8 minus 50 sine 30, and we're going to get a normal force value of 14.2, which means now our force of friction is simply the friction coefficient, 0.20, times the normal force we just got, which is 14.2, and that is going to give us a force of friction of 2.84. Find the acceleration, it's simple from here now, because we have a net horizontal force of F cos theta minus, because it's opposing, the force of friction equals max. So if we combine these, we're going to have 50 cosine of 30 minus 2.84 equals our mass of the block, which we know is 4, times our acceleration. Here we're going to get a net forces value of 40.46 newtons equals 4a. To find the horizontal acceleration, we just have to divide 4 by both sides. This is going to cancel out, which gives us the horizontal acceleration as 10.11 meters per second squared. To find the speed before hitting the spring, we have to use a kinematic equation, which states that the final velocity squared equals the initial velocity plus 2 times acceleration times the displacement. So our final velocity, we don't know yet, so that's going to be our unknown variable. We don't have an initial velocity, so we're just going to cut that out. 2, our acceleration we just found out is 10.11, and before hitting the spring is going to be 5 meters, so we're just going to plug 5 in. We're going to get a velocity square value of around 101.1. So to find velocity alone, we're just going to have to square root both sides, which can give us 10.05 meters per second as our velocity value before contact. To find the max spring compression, we have to use the work energy theorem, which says that the net work equals the change in kinetic energy. So what change in kinetic energy do we have? Well, we have our final kinetic energy where it's max compressed, where this box right here is not moving at all because it's compressing this at its maximum point. So the kinetic energy there is going to be 0 because its velocity is 0, so hence its kinetic energy is 0, minus the initial kinetic energy, which is going to be 1/2 4 times V final equals 10.05 squared. So our change in kinetic energy here would be negative 202 joules. And the reason we have to use the work energy theorem is because work can be modeled as the forces applied to the spring at a certain position, where the spring and the block of the force here is on the same position, because after it's traveled 5 meters, it is here. So the displacement of the box and the spring after that would be the same. What work is at play here? We have F cosine theta, and then our displacement value, which is going to be the same, I'm just going to call it x, minus the force of the friction, which is going to be FFX, is going to be the same variable. Finally, we have the work of the spring, which is going to be 1/2 kx squared because it's compressed. Let's figure out these values. We have force times cosine of 30x minus the force of friction, which we already have, is 2.84x, and we have the spring, which is 800 newton meters, and we have our x value, which we still don't know. I have here 40.42x minus, this is going to be 400x squared, all equals negative 202. And now what we notice here is that it is actually a quadratic equation, because if we add 202 on both sides, we can see that there is a c value, we have an a value, and a b value. So to find x, we can actually graph this. Using the function we just got there, we can graph it. So we're just going to hit graph entry edit, and our function was 400x squared minus 40.46x minus 202, and that's going to equal 0 in the end, so it's a quadratic equation. And we're going to be given this parabola here. All you have to do now is just add a function at y equals 0, because we're trying to find the x-intercept where x equals 0, and then we just have to hit analyze graph, find the intersection. We have to find the positive intersection, and that is going to be right there, 0.73, and that's our answer. We got that x equals 0.763 meters, and now the question is asking us to find the angular frequency. Well, we have to remember the angular frequency equation is root of spring constant over the mass of the block. So here we go. The angular frequency in this situation is going to be root of 800 over 4. And that's going to give us an angular frequency value of 14.14 radians per second. Finally, putting it all together, the simple harmonic position function of the diagram is going to be x of t equals the maximum amplitude, which we found is 0.763 times cosine of our angular frequency there, 14.14, and t. And yeah, that's the video. Thank you for watching.